So we are continuing this class about chemical reaction with few substrate in a microdomain. So now we have seen before how to derive the Markov equation, and at this stage we are going to solve them at steady state. So steady state means that the probability pk of having k substrate, so this is pk of t, which we said was the probability that the number of Sm molecules was equals to k at time t. We're going to suppose that this is at equilibrium, so the time dependency is 0. And then we get an ensemble of equation that we need to solve. That let me I will just rewrite the generic term, which is lambda S minus M S minus K M minus K plus K minus 1K. So this is pk minus this plus lambda S minus K plus 1 M minus K plus 1 pk minus 1 plus K minus 1 K plus 1 pk plus 1. This has to be equal to 0. So and remember, we have the first term, which basically can be written as P1 equals lambda ms, those are the total number of M and S molecules, divided by K minus 1 P0. And actually what you can use this to write an induction equation. And so you can extract from this, from the master equation, you can extract P2 as a function of P1 and P0 and replace P1 by this value here. And you do this in general, and what you can see that is that pk can be written as lambda to the power k factorial k minus 1 to the power k multiplied by P0, and this is multiplied by the product of 0 to k minus 1 of M minus I S minus I. So I leave this is an exercise that everybody can do. Just write the equations and replace. And of course then we have to use the normalization condition, which said that the sum of the pk has from 0 to S, this has to be equal to 1, and this defines precisely P0. And that's it. And then this allows us to have a full description of the steady state. And from this you can calculate anything you want. For example, you can calculate the mean. What is the number of mean NS? Right? So the mean is just the sum of kpk from 0 to S. You can calculate any moment of interest. You can calculate the variance. For example, you have sigma squared which is ms squared minus the mean squared ms squared, right? So this is just k squared pk minus the sum of k pk squared. And any moment of interest can be computed this way. So if you're interested in this, I recommend, first of all, there are 3 interesting references. The first is the book of Saati about queuing theory. The second book is the Carling-Taylor, the introduction about first course in stochastic processes. Carling-Taylor. So there are 2 books which I recommend. And then there is our paper in Journal of Chemical Physics, Holcman, which describes more specifically all this calculation, and we give another method. So maybe I want to discuss one more thing before switching to another topic on this. Is we've seen that these methods can be applied when the rate here is constant. If the rate is not constant, then we have to look at what happened during time t and t plus delta t. And still, you can use the methods with the rate lambda, which is time dependent. Of course, the equations becomes more difficult to approach. I mean, to solve them and to look at the different moments. All right. But this is important because this happens in biology, that you can have a rate dependent, time dependent process. Okay, so let me now give some example of application. So this was motivated by the following fluctuations. We had a domain where you had binding sites here, and you can modulate here the number of molecules that you're injecting, the capital M. And you see, as a function of M, you have a fluctuation which is very small, and as you start increasing this, the modulation, the fluctuations is increasing, and then finally decreases. So this is exactly the process we have studied. We had to look at the variance sigma as a function of M can be found by solving the equation we previously wrote. And so this is an example of cyclic GMP fluctuation in a photoreceptor. This is to understand how many channels are open. So this is for rod photoreceptor, and this is to estimate the number of bound channels, and this is due to the fluctuation of molecules binding and unbinding from site. And this is this is the experimental data. And usually this is approximated by a parabola. That is, people are using basically m alpha m minus beta m squared for this fitting. And so this is our analysis, where we found that actually here there should be a long tail that doesn't go back to zero like it is proposed here, but rather do something like this, as shown in here. So this is the correction due to our theory that we discussed here about the stochastic chemical reaction. And I think this is important if we want to study fluctuations, for example in cones. This process might be important. So the conclusion is that this analysis, our analysis, can explain the fluctuation, or can be used. The analysis can be used to study the noise fluctuation, at least the amplitude in cones, which might be even more relevant than in rods. Alright, so now I would like to move on to another topics, which is how to study the mean time to a threshold. So let me explain what that means. Suppose, as we have seen previously, you have a number of substrate. They are located on the surface of a domain, and you inject molecules here that are moving by Brownian trajectory. So this is an example. This is another one. Another one. So you have molecules. Suppose you have m of them. M moving molecules. And now let's ask the following question. How long do you have to wait for having the number of bound Sm equals, let's say, to 5 molecules or 5 bonds, so let's say a given number k given, let's say 5 or 7. So what is the time t? The first time you have to wait when you start. Suppose at time 0 this is 0, there is no bound. How long do you have to wait for this to happen? So we can formulate this time as follows. This is the first time, such that m or Sm equals a threshold t. And of course we're interested in the meantime for this, how to calculate this time. And why this is important, because you can there are many situations where a cell has to transform molecular event into a cellular event, a physiological event, and this can be measured exactly when this happened, when the number of Sm molecule equals a critical threshold. You can think about induction of plasticity inside the dendritic spine. You have a flow of calcium. You have critical molecules here that are, let's say, calmodulin or CAM kinase 2, depending on the level of complexity of the cascade of chemical reaction you are studying. So let's say CAM kinase or CAM kinase 2, which, you know, bind calmodulin that are bound to calcium. So you're interested in when calcium flows in, how many of these CAM kinase 2, let's say, are bound to a calmodulin that contains 4 calcium. And we can think, we can hypothesize that when this number, let's say, equals 5 or 7 molecules, any threshold of interest, then this is the this is a message to induce changes, but not molecular changes, cellular changes that will lead to a change, let's say, in the shape, or changes in the number of important molecules that are inside dendritic spine. All right, so this time can be calculated, and I would like to discuss what's the link between this and the Markov chains we just discussed. So by definition, the probability that the time, so the probability pt of t, that the time probability that the time has been reached, that is the threshold has been reached, is this cumulative probability density function. And by definition, the mean first passage time is the integral from 0 to infinity of t ddt of probability that tau t is less than t, which by integrating by parts is equal to the integral from 0 to infinity of 1 minus pt of t dt. But by definition, due to the normalization condition, this is exactly the integral from 0 to infinity of the sum of pk of t delta t from 0 to t minus 1. Right? Because by definition, the state, we'll define the state in a second, that the sum of the pk of t equals to 1 from 0 to t minus, from 0 to t. Okay, so now the interesting things to calculate, the interesting quantity, will be the integral from 0 to infinity of pk of t delta t, which we are going to call ak. And so for this, we are going to see how to modify the previous equations. So it is true that if we have a Markov chain, we start with 0 bound, and then we can make transition to 1 up to, let's say, t minus 1 or t minus 2, then we have t minus 1 and then t. So once we make a transition here to this state, it is absorbed. So the state here to come back is 0 flux, right? And so now you can go, of course, if particles can detach when they are attached, you have a rate to go from t minus 1 to t minus 2. But now what we have is we have a Markov chain truncated at the threshold capital T, right? And we need to precisely write these equations. So how shall we do this? We can start with the Markov chains that we had and write pk, which is minus m minus k s minus k plus k minus 1 k. This was pk plus k minus 1 k plus 1 pk plus 1 plus lambda m minus k plus 1 multiply by s minus k plus 1 multiply by pk minus 1. And then what we need to do is we can integrate this equation, everything from 0 to infinity dt, right? So we can integrate everything. And so what do we get? We get pk infinity minus pk of 0 equals, so basically the same thing. And remember that we said that pk from 0 to infinity equals ak, which is time independent. So it's mk s minus k, and there is here lambda plus k minus 1 k ak plus k minus 1 k plus 1 ak plus 1 plus lambda m minus k plus 1 s minus k plus 1 multiplied by ak minus 1. So what happened? Okay, the first term depends on the initial condition. So if we just take that pk of 0 equal 1 and the rest is 0, that is nothing is bound, this is usually 0. So now except the last one, the absorbing state is the state pt. So this is also 0, except we'll see for k equals t. Actually, let's do now k equals t. So the rate to make a transition to t, so nothing is coming from t plus 1, everything is coming from t minus 1, right? So what we need here is the rate, so pt infinity equals, so we need to write it's coming from so k plus 1 there is nothing, so it comes from lambda m minus t plus 1 multiplied by s minus t plus 1 multiplied by pt minus 1, right? because nothing here can come back from once we are in T, there is no rate to go back to 0. You cannot detach, so you're absorbed. Now you can write the equation here for K equals T minus 1, right, which will give an equation between I'm sorry, this is not PT, this is A, T minus 1. So this will give an equation between AT minus 1 and AT minus 2, right, because nothing can come back from T. And actually this, so the equation will be PT minus 1 of infinity minus PT minus 1 of 0. So everything here is 0, this is 0, and this is 0. So this is equals to minus lambda m minus t plus 1 minus t plus 1 multiplied by s minus t plus 1 plus k minus 1 multiplied by t minus 1 multiplied by a t minus 1. This is not clearly readable, so let me rewrite it. So this is plus k minus 1 t minus 1 multiplied by at minus 1, and this is everything multiplied by this, plus the term coming from t minus 2, that is the transition rate. Now we have just written this, plus lambda m minus t plus 2 multiplied by s minus t plus 2 multiplied by at minus 2. Alright, so this ensemble of equation, we get an ensemble of equation for AK and the rate, so this gives another equation which is the transition from the state from the t minus 1 rate to the t minus 1 state to the t state. And basically the ensemble can be solved, for example, if there is no, of course, when there is no backward rate, then the mean first passage time here can be calculated. This is the sum of the AK from 0 to t minus 1. And this is just simply the sum of 1 over lambda k, where lambda k is the rate to switch from state k minus 1 to k. Let me write it more specifically. So the time to threshold is the sum of 1 over lambda k. So the lambda k is the transition rate from k minus 1 here to k, which as we have seen has to do with the lambda k is just m minus k lambda n minus k. In general, when k minus 1 is not 0, then the formula is quite complicated, and I will give it to you and refer for the calculation to the paper. This is the sum from j equals 0 to t minus 1, k minus 1 divided by lambda to the power j, multiplied by the sum from k equals j to t minus 1 of factorial k divided by k minus j, m minus k minus 1 factorial, s minus k minus 1 factorial divided by m minus k plus j factorial, s minus k plus j. Alright, and so let me show you what this gives. So this is a simulation as a function of the threshold t. So you can find all of this graph and analysis in the paper of Can Dao-Duc and myself, David Holcman, and this is Physical Review E, and this is the paper is 2010. So we did here the Brownian simulations, and look at the mean first passage time as a function of the threshold. And you can see this very nonlinear phenomenon where you see that, so this is tau t, is a nonlinear phenomenon, and actually we derive that in some cases it can go like a t squared, and there's here plus corrections. So this correction, you have to look at precisely what they are, depending on the regime, on the different time constant. What we did is, I mean, there is more into this analysis that you need to look at, is the what happened when there is a leak that we already discussed. You can also find some approximation for the probability that the number of bounds ever reach a threshold t once particle goes, and they can move by Brownian motion, but they can miss the target. So what's the probability that you get the number of bounds after your process is done? So you have to integrate from 0 to infinity, or the time it takes for particles to enter, to calculate this probability. Alright, and as we already discussed, there is many application of this to the synapse. It's quite more complicated because here you have to include more into the cascade of chemical reaction. You don't have only one player, which is one molecule that enters and leaves, but you need to have an intermediate where calcium binds to calmodulin, and actually this can happen 4 times. So you can continue the equations up to calcium, calmodulin, and it can bind to 4, and then calcium, calmodulin molecules, which can move by diffusion, can bind to cam kinase 2, and these to form an important. So you have this molecule which has which is a holoenzymes, which contains actually 12 sites, but each site contains 6. 1, 2, 3, 4, 5, 6. You can have one of these molecules bound to this calmodulin kinase 2, which can induce a site which can have a phosphorylation. Alright, so there is still work to do to use our theory in this context and to calculate the number of bound, a threshold for the number of cam kinase 2. So I think we're going to stop here for this application. Again, I refer to the papers, one of Can Dao-Duc, and we have a recent paper that is in collaboration with Kevin Burridge, that will appear soon. Kevin Burridge, Ken Dowduck, myself. And we use the concept of threshold of chemical reaction in the case of scRNA. So this is a new paper, scRNA, silence RNA, how they modulate messenger RNA in the nucleus. Alright, so thanks for your attention.